How many did this? I3 minus sp3 dehybridized central iodine atom, or central atom, which happens in this case to be the I atom. When you write a Lewis structure, like this one, how can you determine the hybridization for the central atom?
By looking at the bonding non-bonding pairs?
Well, tell me how to look at them.
So,
I'm looking at them.
okay, so for every IR bonded one, that kind of tells you the. Explain it.
Wait a minute. This is a simple task. You should have learned this in 2045.
Count the number of bonding and non-bonding pairs in this rosy.
Be careful. What if I got double bonds and triple bonds?
Count the number of bonds as well.
What kind of bonds?
Well,
You did this in 2045.
Count the number of atoms of separate atoms bonded to. All double bonds. It's a single double triple.
See this directive? Everything you need to know about writing Lewis structures and interpreting the Lewis structure in order to determine hybridization in geometry is explained in detail in chapter 23 of our notes. After you write the Lewis structure, no, we're not counting areas. I mean, I want this to be as simple as possible. You might be getting at the idea. The word I'm looking here is the word for this Greek letter. What is it? Sigma. Good. To determine hybridization for an atom from a Lewis structure, central atom. There are other rules which apply to peripheral atoms. We'll talk about that later. Here's our central atom. You count the number of bonding sigma electron pairs at every bond site. How many bonding sigma pairs are there? How many sigma bonds at a bond site? Nope. How many? How many? You ever see a Lewis structure where you got 5 bonds between atoms? How many sigma bonds at each and every covalent bond site? Do you know what a bond site is? What's a bond site? What the hell did you do in 2045? I'm not picking on you folks. This stuff should be second nature to you. And arguably, this is the most important thing you should do in 2045. Yet each term, when I get together with my 46 students and I go through this, I find out they can't do it. I don't know what's going on. But I can tell you, if you paid attention to assignment 6 and 45L, you learned this. The trouble with 45L is we're operating in partnerships. That's the result of a very stupid decision by the administration of this university. This is fun because all this is going to be on the internet. And I don't give a damn. We should not have more students enrolled than we can handle from an educational success or an educational achievement standpoint. And we have to have you work on an individual basis in laboratory if we're going to achieve that. It's not your fault we have this. At each and every covalent bond site, there's one and only one sigma bond. So at every bond site you examine, there's a sigma bond. There are a couple of rare and unusual exceptions to that, found in coordination chemistry. which we'll talk about at the tail end of this course, but not now. Never mind the exceptions. Take this as a rule. At every covalent bond site, the juncture between two connected atoms, there's a bond site, there's a bond site. There's two bond sites in this species. There's one sigma bond, always and only. And since non-bonding pairs are part of the sigma system, hybridization considerations must include non-bonding pairs. So to make that as simple as possible, I count non-bonding pairs as sigma pairs. The theoretical people go into horrors over this, because sigma language means bonding, and non-bonding pairs are not bonding. But I'm trying to make this game as simple as possible for you folks to play successfully. At every bond site, one sigma bond. That means one sigma pair. And non-bonding pairs are sigma, period. So let's look at this atom. How many sigma pairs? 1, 2, 3, 4, 5. And once you count up the number of sigma pairs for a central atom, you can immediately determine, based on what you learned in 2045, I hope, hybridization scheme. Because if you got 5 sigma pairs, you need to hybridize how many orbitals to provide a home in space, so to speak, for these atomic electron pairs. How many orbitals do you have to hybridize to provide a home in space for the 1, 2, 3, 4, 5 sigma pairs in the valence environment of this central iodine atom? How many orbitals do you have to hybridize? 5. That's it. You got the number of sigma pairs, you know how many orbitals you have to hybridize. So now all you got to do is pay attention to the hybridization schemes, which I presume you learned in 2045, but after this response to the last consideration, I'm not sure. What's the simplest hybridization you looked at? What is it? SP. That's a hybridization of 2 orbitals, an s orbital and a p orbital. You know how to make hybrid orbitals? You make hybrid orbitals just like you make sausage in the butcher shop. I'm not kidding. I want to make beef pork sausage. I get out my meat grinder. I put in a pound of beef and a pound of pork. I jam them into the meat grinder. I'm hybridizing. Now I collect. How much sausage do I collect? 2 pounds. Could I put in 1 pound each? Just like if I hybridize 2 orbitals, how many hybrid orbitals do I get? 2! This is not a tough game. But the sausage I get is now 50% beef character and 50% pork character. It's no longer pure beef or pure pork. Okay? So I hybridize B beef and P pork. Now I'm going to hybridize orbitals. S, this perfectly spherical thing, with P. What's a P orbital look like?
Dumbbell.
A dumbbell. 3-dimensional figure 8, if you want. So I jam my s orbital and my p orbital into my orbital grinder. I'm not making sausage now, I'm now making hybrid orbitals. I turn the crank. I get out 2 orbitals, because I put in 2 orbitals. But neither of the orbitals I get are any longer pure s or pure p. I label it sp because the orbitals which I get are now what percent s character? And what percent p character? That's it. Did you learn what a hybrid orbital looks like? Because I don't care the label on the hybrid orbital. SP, SP2, SP3, SP 17,000. They all look the same. You learn that? Never mind the shape of a hybrid orbital. I'm not responsible for it. But they all look like this. That's the bonding part. That's it. This is not hard. But if you don't present it properly, students sit there and say, what the hell are you talking about? I know this. So now we know how to make hybrids. Here I got to hybridize 5 orbitals because I got 5 sigma pairs to account for. So which orbitals do I hybridize? Now I have to know one other thing. I have to know that in an energy level, where if present there is an S sublevel, which is a single orbital sublevel, a P sublevel, which is a sublevel of how many orbitals? 3. And a D sublevel, which is a sublevel of how many orbitals? 5. That these orbitals orient themselves with respect to relative energy. In what fashion? If you're an electron and you move into energy level number 3, which is the lowest energy level that contains S, P, and D sublevels. 3S, 3P, 3D. And in front of all these sublevels you see a vacancy sign. Well, Mr. or Ms. Electron, in which of these orbitals do you take residence? S, P, or D? S. Why? Because you'll be most stable. And on a time average basis, most stable means you'll be where in space relative to the nucleus? Yes! And after the S orbital is filled up, you move into P. And you don't move into D until the P orbitals are used up. Okay? That's why when I make hybrids, the first I make is SP, the second I make is SP2, the third I make is SP3, which symbolically looks like SP cubed, but it's SP3. And then I finally involve D. Because after I've ground up 4 orbitals, using S and the 3p orbitals from the p sublevel, which is the lowest energy orbitals in an energy level, I don't have any more of these. So I now got to go to the next orbitals available. That's D. So to hybridize iodine here, because I got to count for 5 sigma pairs, I got to hybridize my S, all of the p's from the p sublevel, which is 3, and one of the d's. So it's sp3d. Because I label the hybrid in terms of the orbitals which I use to create the hybrid. That's it. How many hybrids can you make from an S sublevel, a P sublevel, and a D sublevel? How many hybrids can you make? 9 of them. Did you learn that? Because once we start using these D's, we can make sp3d, sp3d2, sp3d3, sp3d4, and sp3d5. And if we wind up with an atom that's got 9 sigma pairs, that's exactly the game we'll play. Because orbitals ain't real. They're ideas we cooked up to help us understand bonding and structure. These are mathematical artifacts. They're not real. But they help us understand bonding and structure. That's why we use this game, this idea. Now then, the next part of the puzzle is geometry. If I scramble 5 sigma pairs in the valence shell of an atom, what geometry is exhibited by the 5 sigma pairs after they quit scrambling? After they assume positions in the valence shell, which is a spherical shell wrapped around the nucleus of the atom in question. After these 5 sigma pairs quit scrambling, what geometry is exhibited by the 5 sigma pairs? What geometry corresponds to minimum repulsion among and between these 5 sigma pairs? Trigonal bipyramid. How about that? If I go to 6 sigma pairs, I get octahedral. If I get 7 sigma pairs, there are 2 possibilities. The simplest one is what? Trigonal bipyramid for what we got here. It's trigonal bipentagonal. You know what a pentagon looks like? 5, 1 above and 1 below. There's your trigonal bipentagon. How about that? 8 sigma pairs. You know what a cube looks like? Is a cube the best geometry for 8 sigma pairs? Not really. Cube. You know what a cube looks like? 6-sided object, and each face is a perfect square. You play with baby blocks when you were a kid? Were your baby blocks cubic? Mine were. Kids today are playing with computers. That's stupid. I mean, that's stupid. Really stupid. You know, if you were searching the internet to learn chemistry, then I'd say it's wonderful. But I see what the kids are doing. They're playing games. Damn games all the time. What the hell intellectual enrichment are you getting from this? Nothing. Unless it's a game like chess. Then you're getting intellectual enrichment. This 8 sigma pair arrangement is a square antiprism. I'll tell you more about that one later. But if you're curious, look up square antiprism. And you find out you take a cube and hold the top or bottom square in place. If we hold the bottom square in place, we'll take the top square and rotate it 45 degrees. Now you've got a square antiprism, which provides larger bond angles and a greater degree of mutual separation among and between the 8 sigma pairs, which gives us the best geometry you can have. You should learn all of this in 2045. Everything I just said. So I'm telling you now, you are responsible for these Lewis pictures, interpreting them in light of hybridization and geometry throughout this gathering. So if you need the review, let's not worry about what you did or did not get from 2045. Let's get at it. I'm telling you, it's in chapter 23. Now for this picture, how do you realize the 3 non-bonding pairs all lie in the equatorial plane of this trigonal bipyramid? The result of which is that you get a linear geometry for the I3 species. Why is that? Don't talk to me about iodines. Talk to me about electron pairs. Because it's all dictated by Coulomb's law. Did you hear about Coulomb's law in 2045?
The 3 electron pairs are all found equally, so it keeps it in.
Well, that's kind of close. Why not this?
Because bonding pairs of electrons have more repulsive force than...
They do?
Do they?
No. Not unless there are multiple bonds.
Oh, okay.
The greatest repulsion is between bonding electron pairs?
Nope. Unless there's multiple bonds. We don't have any multiple bonds here. Greatest repulsion is among and between non-bonding pairs, because a non-bonding pair is a region of electron density that's stabilized by one nucleus. The nucleus of this atom. But the bonding electron pairs are each mutually stabilized by 2 nuclei. This atom and this atom. That makes the electron density associated with the non-bonding pairs greater than the electron density associated with the bonding pairs. You didn't do that in 45 either? This is a hoot. Like hell it is. It's a travesty. But it isn't your fault. But I'm telling you now. You go there. It's in your notes. You got the notes? Put this information to use. Because structure is the most important property of any species, and the Lewis structure game is the simplest way to get its structures. That's why you got to be good at this. And I want you all to be good at this. And I'll do everything I can to help you be good at this. But you got to do your part too. You can watch me paint all day long. I ain't going to make a painter out of you until you put that damn brush in your hand and start painting. Until you sit down at the piano and start playing, you're not going to be a pianist, you're not going to be a painter. And you're not going to be a successful student of chemistry until you start doing this stuff on your own. And that's what I need you to do. Because I want you all to be successful. But if all you do is sit and listen, you will never be successful. Let's move on. Let's get chapter 17 finished at long last. You looked at this equilibrium system earlier in chapter 17, didn't you? Specifically, in Tuesday's discussion class gathering. Now, this equilibrium system, as you examine it in Tuesday's discussion class, was written in the opposite direction. So what? Still an equilibrium. It still involves the same materials. How does the equilibrium constant, the value for the equilibrium constant for this reaction, compare to the value for the equilibrium constant for this reaction if I write it the opposite direction? Well then, this would invert, which means the value would invert. But if I choose to study this equilibrium system under some imagined wonderful conditions, which gives us the simplest possible equilibrium constant value of 1.0, then it wouldn't matter numerically. But if the K value is anything but 1, then the K value is going to change if I write this in the opposite direction, because it's going to be 1 over. All right? We're studying this system. It exists in this piston cylinder gadget. In this piston cylinder gadget, I have nitrogen, hydrogen, and ammonia in equilibrium with each other. If I stipulate that in the piston cylinder gadget, with a total volume of 1.0 liters, there is contained within a molar concentration of nitrogen of 1.0, molar concentration of hydrogen of 1.0. What's the molar concentration of ammonia?
1.0.
How about that? I purposely pick or construct these problems so that arithmetically they're as simple as possible, because I want you to understand the chemistry. And after you understand the chemistry, then I don't care what I do with the numbers, you'll be able to handle it. But if I start with complicated numbers and try to get across the chemistry, it makes it all the more difficult. All right, now we're going to apply a change to this system. I'm going to take a hold of the handle on this piston, and I'm going to shove it into the cylinder until I've reduced the system volume to 0.50 liters. And then I'm going to lock the piston in place. Are we understanding the change?
Small question, this is kind of dumb, but is the equilibrium for that reaction really 1? Or are you...
We don't care. That's immaterial and irrelevant. I picked this system because of the system you've already looked at, and because of these coefficients. You're asking me, can I in fact study this system at a condition where the Kc value is 1.0? I don't know and I don't care. That doesn't matter. We'll worry about those points later when you as a chemist go into the laboratory and start doing chemistry. Okay? Then you'll have to pay attention to that kind of information. What we're doing now is to show you how, when you go to the laboratory, you can deal with any information you collect. But your question is fine. Okay? So in this pot, if the molar concentrations of these things are each 1.0, and the pot volume is 1.0 liters, how many moles of each of these things do I have in the pot? That's really tough, isn't it? 1.0 moles. Now this thing would be at one hell of a high pressure if I got 1.0 moles of each of these gases in a volume of 1.0 liters. But let's not worry about that part either. We recognize the change we apply to the system. We're going to squeeze the system by raising the pressure until the resulting volume is 0.50 liters and lock the piston in place. The question is, when we apply this change to the system, what happens? The first thing that happens, as soon as I apply this change, is the equilibrium is killed. Here's where the stupid textbooks start talking about the equilibrium shifting. The hell with that. No respectable equilibrium in its life ever shifted. It's the most stable thing it can be. Now, there are finer points to this, but we don't care about that. Your job now is to learn. So, at the minimum, we realize as soon as I apply the change, the equilibrium is killed. What reaction will occur in this system to reestablish equilibrium, given that we did not add or subtract any material, nor introduce any new materials to the system?
In favor of the reverse reaction.
I got to vote that to reestablish equilibrium, the reaction which occurs is this. Is this correct?
Yes.
That's correct. How do you know this?
Because since the pressure change, it'll go in the direction that has, since the pressure increase, it'll go to the moles with less molecules.
That's right. Does it not seem reasonable to you that the smaller quantity of material lives more comfortably in the smaller volume, the smaller amount of space? And vice versa, if I take this very same system and change it by increasing the volume, the reaction that would occur to reestablish equilibrium is left to right. Now, this can explain from a detailed kinetic standpoint. It's in Chapter 17. If you read Chapter 17 discussion, you know this. But let's proceed with the analysis. We know the reaction that occurs to reestablish equilibrium, which means relative to my initial starting quantities of 1.0 moles each of nitrogen and hydrogen, these mole quantities are going to, on reestablished equilibrium, get larger or smaller? Smaller. And ammonia is the stuff being made, so that stuff will increase in terms of mole quantity. Now then, how do we proceed algebraically to attack this? The simplest thing to do is to use the equation for the reaction as a guide. That's the simplest thing to do. So I'm looking at this reaction equation. As I read it left to right, this reaction equation tells me if 2 moles of ammonia fall apart completely by this process, I will produce 1 mole of nitrogen and 3 moles of hydrogen. If I look at it in the opposite direction, if 4 moles total of nitrogen plus hydrogen, 1 mole nitrogen plus 3 moles hydrogen, combine entirely, I'm going to wind up with 2 moles of ammonia. So I use those coefficients as my guide. We'll start with nitrogen. And see, the coefficient is 1. So I'll use X to represent the amount of nitrogen which is consumed by this reaction to reestablish equilibrium. How much hydrogen is consumed? How much ammonia is made? See? That's easy. You let that thing talk to you. Because that's the recipe. Did you learn how to read equations for reactions in 2045? An equation for reaction is a recipe. That's all. And I just read the recipe. It's an if-then clause. It's not a guarantee. A reaction equation doesn't tell you anything about conditions which you need for the reaction to go. Doesn't tell you any of these things. Now then, when we have the convenience of mole amounts being contained in a 1 liter volume, then mole amounts and molar concentrations are numerically equal. But as soon as I change the volume from something other than 1 liter, now I've got to pay attention to volume. Because my equilibrium constant expression is not in terms of mole amounts. It's in terms of concentrations. So I have to convert these mole quantities, written here, to molar concentrations. So I simply take the mole quantity, which we have recognized to result by the reaction that occurs to reestablish equilibrium, and divide by the volume. For convenience, I'm going to leave out the unit. We know it's liters throughout. Now myself, I don't like dealing with fractions. So I'm going to take this and divide through by 0.50. When you divide something by 0.50, what are you doing to that something? You're doubling it. So I'll rewrite this as 2.0 minus 2.0x. And this becomes 2.0 minus 6.0x. And this becomes 2.0 plus 4.0x. There we have it. So now I'm going to go back to my equilibrium constant expression, where I have it written chemically up there. Now I'm going to write it algebraically. There's the nitrogen concentration. There's the hydrogen concentration, cubed. And there's the ammonia concentration, quantity squared. And now we get to the $64 question. How do we solve this thing? Because we are going to be looking at problems like this throughout. You're going to look at problems like this very often in quantitative analysis class if you go to study analytical chemistry. And you have to realize, if you try to solve something like this by brute force algebra, you're going to have one hell of a mess on your hands.
That's why we have robots do it.
No, no, no. There ain't no robots in here, just you. We're not passing this buck to some robot. You're the one that has to do it. And now we're going to show you how to do it, because it's easy. But I'm telling you, if you take, for example, this top term and expand it, you're going to have x to the fourth power up top. Such problems are difficult to solve from a rigorous arithmetic or algebraic standpoint. But if you put on your thinking cap and do some simple mental arithmetic, you'll see this is not hard to solve at all. How do we do it? Let's take a look. Consideration number one. Never mind the exponents. We're looking at the concentrations. Which of these concentrations is smallest? Is it this, or this? Which one is smallest? This is nitrogen. Hydrogen. Ammonia. Which of these concentrations is smallest?
Hydrogen.
Hydrogen, of course. You realize X represents something that's real? These are material entities. This is no longer a problem strictly in algebra class. These are in fact concentrations. So now I have a question. Max possible value for X is, fill in the blank. I accept that, but I don't want it as a common fraction. I want it as a decimal fraction. 0.33. That's correct. Do you all agree with that? Good. I'll write an exclamation point after that because it's important. We haven't done anything fancy, but we've recognized these terms represent concentrations, and concentrations, for an equilibrium to exist, can never be 0 or minus. How tall are you? -3. What the hell does that mean? So, I haven't done anything fancy. And I already got my value for x in a box. It cannot be bigger than 0.33. And it cannot be smaller than 0. The arithmetic folks, or calculus people, what do they call this? A range. I got the true value for x in this range. Since I got 0.33 to 2 decimal places, I'll write my 0.00 accordingly. Now then, let's proceed to solve. Now's when your pocket calculator comes in quite handy. To solve this, my directive to you is first start with a simple value for x that's in that range, so that you can, with this simple value for x, calculate the value you get for this term right here. You're going to evaluate this term on the basis of your speculated value for x and see how the value for this term compares to 1.0. Because when you put in the correct value for x, this is what you get. Pick me a simple value. 0.10. 2 sig figs. We got to do this arithmetic to 2 sig figs because every component from an arithmetic standpoint for this system is expressed to 2 sig figs. All right, all right. Try 0.10 equals x. Now let's look at this. This becomes 1.8. This becomes 1.4. Quantity cubed, and this becomes, get out there, 2.4 quantity squared. So now you get out your pocket calculator, you take 1.8 times 1.4 quantity cubed divided by 2.4 quantity squared and see what you get. Gives, what'd you get? 0.858. What did I get? I don't know, I write this stuff, scribble all over the place. I get 0.86. What's this tell me? 0.86 is not quite 1.0.
The numerator is too small, so
I want to know about x. Is x tried at a value of 0.10. Too big or too small? Too small. Because this term tells us okay, that as x gets bigger, what happens to the terms up top? As x gets bigger, the terms up top get smaller. Because I'm subtracting a larger value from these quantities. And as x gets bigger, what happens to this term? This term gets larger. So as x gets bigger, this fraction gets bigger or smaller? Smaller. So x is not bigger than 0.10. Because the bigger I make x, the smaller this fraction gets, and I've already got a value, 0.86, that's smaller than k. So you got to let this stuff talk to you. And one of the things that I know most, if not all of you folks are tainted with, again, it's not your fault, is arithmetic skills in high school, grade school. If you came from a high school, for example, or in math class, the teacher on a regular basis is having you do stuff like this with a pocket calculator, I'm going to horsewhip that person. And if they do it again, I'm going to hang them in public. And then we're going to get this educational process fixed. Not with all this hoo-ha that I'm hearing on TV. from these politicians who don't know a damn thing about the educational process. And that, I will say, also applies to Mr. Arne Duncan, our Secretary of Education. He talks about how students need to study this stuff until they have mastery of it. Mastery of it? I've been in chemistry my whole life. I'm nowhere near being a master of it. What the hell is he talking about? These people need to deal with something called fact and truth, and they avoid that like the plague. That disgusts me. But in here, it's different. Here, facts and truth is what will be our guide. Exclusive guide. So we go back to this. Oh, you'll hear more sermons about the arithmetic stuff as we proceed. We go back to this problem. We've recognized that x is a value that's a little bit smaller than 0.10. So I'll try x equals 0.090. And with x equals 0.90, I'm going to write this over here. For x equals 0.090, our term, that's this. Here's our term. Equals 1.017. I got to cheat on significant figures until I get the right value for x. Then I'll go back to 2 sig figs. So I see, by golly, I'm awfully close to 1.0. In fact, to 2 sig figs, I am at 1.0. But I got to be careful about this, because for x equals 0.091, because at 0.090 I have got a value which stretched to 4 significant figures is ever so slightly bigger than Kc. So I'm going to try 0.091. And now I get .99999, which is correct. Which x value is correct? The answer is, which of these numbers? 1.017 or 0.99999 is closer to 1.0? 0.99999, and that's it. And we're going to do stuff like this throughout the term. This is what I call the speculation method. But speculation made not on a wild, goofy guess basis, but on an educated arithmetic horse sense basis, where we let this thing called the term talk to us. Pick it up from this point next time where we go into chapter 18.